Cray XMP block diagram analysis. This course is a videotape classroom presentation given by Lonnie Heitke of Cray Research. Before you begin, you will need the following instructional materials. All should be found in the Cray XMP Introduction Course, HTC 0871. Unit number 2 contains the information on block diagram analysis. The reference documentation you'll need is found in Unit 8. You should also have a Cray XMP 2224 chassis map in the front binder pocket along with a Cray XMP assembly language reference card. Cray XMP block diagram analysis unit is divided into 6 sections. Section 1 covers memory. Section 2 covers fetch. Section 3 covers A and S registers. And Section 4 covers vector registers. Section 5 covers I/O and exchange. And finally, Section 6 covers shared registers and additional points. Most of the course sections have 1 or 2 video exercises, which are also found in your course materials. At the appropriate times, stop the tape and work the exercises before continuing into the next section. Once you've completed the video exercise, turn the tape player back on to see the exercise worked out. You'll be able to check your answers on the videotape. At the end of each section, you'll also be expected to complete several unit exercises. These exercises are found in the course materials along with the answers so you can check your work. Now let's begin the Cray XMP block diagram analysis with the course objectives.
All right, so the objectives. The first thing we're going to do is, and hopefully these are in the same order I just talked about. We'll see if I didn't mess up. Describe the overall specifications of the memory, including size, speed, data format, and address format. So that's one of the objectives, and it says with the aid of student reference material upon completion of the course, a student should be capable of. In other words, if I give you a test, you should be able to answer some of these questions. Well, hopefully all of them, but at least some of them, you know. Hey. Number 2, determining the storage modules associated with a word or bit of data given its memory address. Well, that means, in other words, if I give you a failing data bit and an address, you should be able to tell me which module that came from. Describe interleaving and its effect on memory speed. Well, sounds like that might have some effect on speed, I don't know. Interpreting memory parity error information. Whew, I can't even say it, but hopefully I'll be able to tell you how to do it. Describing the main characteristics of all the register types in the XMP. Well, there's the rest of the block diagram. Describing the flow of instructions from memory to the time of issue. Number 8, describing the method that the Cray uses for swapping control from one program to another. There is a distinct method used in the XMP that will do that. Generating addresses for all given types of memory references and determining the conditions that would delay the issuing of a given instruction. So, that's what we're going to be able to do at the end of this 2.5 days. Any questions so far?
Section 1, Memory.
So we're going to begin our discussion talking about memory. on the cray XMP, there are several different sizes of memory available. There's also several different options available in CPUs. Those options are, there is a XMP1, XMP/1. The XMP/1 is a one processor XMP. Now, in other words, the XMP1 looks just exactly like the picture of the block diagram on the walls, in that there's only one of them here. There's one CPU, and that CPU can come with variations in memory size. In other words, we can have an 11, which says it's a one processor XMP with 1 million words of memory. Or we can have a 12, which is a one processor XMP with 2 million words of memory. Or a 14, which is an XMP1, one processor with 4 million words of memory. So there's three different options available in XMP1. And 1 mil. One, 2, or 4 million words. Now, I didn't mention anything about that other than the physical size of the memory. But the XMP1 does use a specific type of memory chip to hold this memory data, and that is it uses a static NMOS chip. And it's a 16K chip. A 16K static NMOS chip. All right. No matter what memory size, it's just a varying number of chips, in other words. It gives you the different sizes. So, that's the first option a customer could order. Or you could order if you got an extra $5 or $6 million laying around you don't know what to do with. If you do, see me. I'll help you out there. But anyway, that's one option. The next option is the XMP... Got ahead of myself. XMP2. Once again, the first number in the designator here tells you the number of processors. So it's an XMP2. There's two processors in there. There's two CPUs in the same mainframe. Those two CPUs have two options, either a 22 or a 24. All right, so two processors, two CPUs, either 2 or 4 million words of memory. $4 million. 2 or 4 million. Now, there's one other option that's available to a customer, and that is an XMP 48. And just like the numbers told you on the rest of the designators here, it's a 4 processor, 8 million word memory. Now, the XMP1 and the XMP2, the CPUs are identical. There are no changes, well, at least very few changes, to make either of these CPUs. You could take modules out of one of the CPUs from a 1 and put it in a 2, and they will work in most cases. Yeah, that is assuming, of course, they work to start with. But anyway, the modules are identical. The memory is somewhat different in that, I haven't told you this yet, but we use a 16K static NMOS chip in the 1 processors. Here, in the 2 processors, we use a 16K ECL memory chip. Emitter coupled logic, bipolar memory chips. So we could take either of these CPUs and talk about them, and it equally applies to both of them. There's a few minor differences, but it's mostly in the memory modules when you get into memory section where the differences apply. So what we're going to do during this block diagram discussion is we're going to talk about the XMP1 and 2 CPU. The XMP4 CPU is quite a bit different. Once again, most of the differences are in memory, but it's quite a bit different than the 2 processor. But this option is available. Once again, it's 4 million words, 8 million words, 4 processors. Almost made an 84 there. But anyway, 4 processors, 8 million words. It is considerably different, even in physical size. It looks different. It's a 12-column machine as opposed to a 6-column machine. It's twice as big. Well, it makes sense. There's twice as much there, right? Huh, how'd they do that? Well, anyway, this also uses the 16K ECL chip. So we're going to limit our discussion over the next ensuing days in these 2 systems, but I did want to tell you about this one, make you aware that it's out there. All right. Now, all of these machines are the same in that their construction is almost identical. We have an aluminum cold bar that we call it, and that aluminum cold bar is going to hold all the modules and make up the mainframe. We take these aluminum cold bars and we put them physically about 6 or 7 inches apart, and they have slots in them. The modules slide then into the cold bars. There's a mechanical connection that you make, and it tightens a wedge cap up against the bottom of the cold plate that the module sits on, and that's how we keep this computer cool. Since we use ECL logic in the CPU, in both of the 1 and the 2, the CPU puts out a lot of heat. And we have to have some way of getting rid of that heat. And the means we use is freon cooling. So this cold bar, the reason it's called a cold bar is it has copper tubes inside this in a S pattern or snaking back and forth in this cold bar. And we have freon running through there. We use R22 as a refrigerant, and we cool that so that the column runs about 70 degrees all the time, approximately 65 to 70 degrees. Now, the inside of the module is running considerably hotter than that because it does take some time for the heat to flow from the center of the module, where there's a PC board, out into the cold plate, or down into the cold plate, and then out into the cold bar itself and be dissipated. But that's how we cool it. Now, since most of you already saw the block diagram tapes, you know that the Cray 1S was constructed similarly. The XMP, the major difference between the XMP and the Cray 1S is that the XMP has double modules. In other words, the modules are actually 2 Cray 1S type modules physically bolted together. They're just like an IOP module in this case. They are physically bolted together. So this module assembly then slides into the cold plate, and we have a picture of what this computer looks like here on the wall. This is called a chassis map. This chassis map shows you the different chassis, and the chassis are lettered. Here at the top of the, upper left-hand corner, there's a D above that chassis, and then it's got a bunch of bank format and write data and module locations down the side, and numbers down the far left-hand side. What this is a module location chart, a chassis map. So there's a D, E, F, G, H, I chassis, and a chassis is just half of one of those aluminum cold bars. There's an aluminum cold bar on each side of the D chassis, keeping the modules in the D chassis cold, or from getting too hot. The bottom half of this column is given a different letter designator. So there's another set of letters on the bottom. It goes P, Q, R, S, T, and U, and that is the other half of the chassis, the other half of the column. So there's 2 chassis in a column. One column is one of those aluminum cold bars, or 2 of those aluminum cold bars with the modules in between. Half of that column is a chassis, and those chassis designators then, there's numbers up the side, so you can go over here and say the module at D55, which is a very upper left-hand corner module, is a 3ZV module, and I will tell you now the 3ZV module happens to be a memory module. And then you can go to anywhere else in the machine and point to I can point to a spot, and you should be able to tell me what type of module is there. Right? For example, at F32, what kind of module is there? Somebody that's sitting next to a chassis map, look at it. Or you do have chassis maps in your handout packet if you want to look at it. But somebody... 3GR? Yeah. Right. Does everybody see how that's done then? So that's the chassis designators. You can go over here and pick a module location then and say, I know that that particular 3GR module, where it's located. And I could go to any other machine now and put it in that same spot. All right. Now, if you'll notice, there's a group of modules there. Remember, it's a 3GR module. I told you these were double modules. There's a group of 3GR modules. From F32 through F46 are 3GR modules. Because of those number and then two-letter designators on that module, the fact that it's a 3GR, you should be able to take that module out of F32, for example, and put it in any other spot in the machine. And it should work. In other words, the logic on one 3GR is identical to all the other logic on every other 3GR. Down in the other chassis, in other words, in the R chassis, there's some 3GRs down there also. Same thing applies there. So there's CPU 0, is physical CPU 0 is in the top half of the chassis, or in chassis E, F, G, and H, or the top half of the columns there. CPU 1 is in the lower half. And those modules, wherever the number and letter designator is the same, they are swappable, I guess. You should be able to pull one module out and put another one of the same letter and number type in there, and it should work. All right. So, I told you there were 1 and 2 processor CPUs. What you have on the wall alongside of you is a 2 processor CPU chassis map. If it were a 1 processor CPU, one of these halves wouldn't be plugged. And in fact, we don't put any modules in the lower half if it were a 1 processor. So there are no GRs in the lower half in the R chassis then. The R chassis is empty for those module locations. That's the difference between a 1 and a 2 processor as far as physical CPU size and differences. Any questions so far? Now, some of the modules in the very center of the machine here are modules that are shared from one CPU to the other. Some of those modules have to be in there. So if you look at a 1 processor system, there isn't a line across the middle there where there's no modules below that. There's some modules scattered on both sides of the dividing line here. And that's because they were some type of module that was needed for intercommunication or shared in some way. All right. Now, back to the memory, I guess, discussion, and that is there are 4 options. 3 options available in a 1 processor, 2 options available in a 2 processor, and we said we weren't going to talk about a 48. Now, since there are so many options, we're going to pick one type and talk about that throughout this discussion, and that type is going to be the 24 system. I will tell you at times the differences and how to go from a 24 to a 22 or what the differences look like, but we're going to spend most of the time discussing a 24, the biggest system. And I guess I don't really know the numbers as far as sales, which one's most likely to be out there. Well, how many address bits do you need to address one of 4 million locations? That's not a question somebody asks you every day, huh? How many address bits you need? More than 1, yes. How many? Anybody? 20 or something. Any idea? 24? It's a little high. 22, you're right. Now, these address bits, we need 22 address bits to address one of 4 million distinct locations. The way we're going to number these is 2 to the 0 through 2 to the 21st. That's 22 address bits. If you start counting at 0, it ends up to be 22. So, I've already told you something about a 4 million word memory, and that is you got to have 22 address bits. Now, the data word of an XMP is 64 bits. And besides the 64 bits of data word, we also have an option or a feature on our memory in that we have error correction. So for that error correction, what we have to do is we have to add some check bits, what we're going to call them. So there's another 8 check bits added on to this 64 bits of data. Well, let's do it this way. So we totally have a 72-bit word that we have to address in memory somewhere, because what we're going to do is we're going to take this data word on the way into memory. We'll create these check bits through some magic circuit. And, well, it's not really magic. It's a pretty straightforward deal. But anyway, we're going to create these check bits on the way in. We're going to store them right along with the data word. Then when we read this location, we'll bring this whole data word, whole 72-bit word out of memory. We'll regenerate those same check bits, hopefully. If we had a data error, when we compare them, we will know that we had an error and be able to correct for it. So we do error correction. We do single-bit error correction on the 64-bit data word, and we do double-bit error detection. So we have secded on that 72-bit word. And we have 22 address bits. So we have 4 million locations plus, it's a factor of, it's 2 to the 21st power, whatever that equals out to, is 4 million, I don't know, some odd number. But anyway, 4 million words of storage, and those words are 72 bits in length. All right? So that blows your IBM PC out of the water, don't it? What we've done with this memory, well, I guess there's 2 ways now you can design a memory. Keep in mind that you have to have a 4 million word memory. There's 2 ways you can design it. You can say, let's take and start right here in memory. Here's a picture of memory. And let's start right here and put the first word there, and then the next, and just pile them right one on top of the other. All right? What we're going to do, if we do this, is we're going to have to, every time we address, we're going to have to wait for the chips. In other words, here we've got, let's say this is 1 chip inside here. We'll put word 1 or 0 in this chip and word 1 and then in this same chip, and 2 and 3 until we get that 16K chip filled. That means we'd have to have 72 of them across this way. And then we'll go to the next chip and just keep on going. That's one way you could design a memory. But is there a problem in designing a memory that way? What?
Slow.
Why is it slow? That's right. We said there was a cycle time on these memory chips, didn't we? We said the ECL, the cycle time was 35 nanoseconds. Well, that's not that much time. That's not that big of a deal, is it? Well, actually, when Seymour designed the original cray 1, the access time for the original cray 1 was 40 nanoseconds. See, he thought that was too much time to waste. And so when they did the enhancement on the cray 1 and made the XMP, they figured, well, we'll do it the same way Seymour did. Must have been a good reason. Hopefully that wasn't their thinking. But anyway, they did. They said, rather than do this, let's interleave them. So if we take this memory, we got 72 chips this way. Let's put word 0 in this chip, but let's go up here and put word 1 in a different set of chips, up higher in memory. And then word 2, and then word 3. What we're doing is we're interleaving the memory. So they said, what we want to end up with here is 32 total banks in memory. In other words, each bank is going to hold a portion of the data words. Altogether, there'll be 4 million, but since there's 32 separate banks, each one must be about, 128K or something like that, huh? I got it written down here. Let me check. Yeah, that's right. 128K times 32 is 4 million. Yeah, that's pretty close. Now, what we gain in this is that we gain speed when we go sequential addressing. When we go from word 0 to word 1, 2, and 3, we can get this word out in 1 clock period. And a clock period on the XMP is 9.5 nanoseconds. In the next clock period, we can get word 1 out. And the clock period after that, we can get word 2 and 3 and 4. And we can just keep cycling. When we cycled all the way through all 32, we'll go back to the bank 0 again. All right? So we've arranged it and divided it up into 32 different segments, our memory. And we do that with the address bits. We said, let's take, well, since we have 32 separate and distinct banks, let's take and have enough addressing here to address one of 32 different locations, or 37 octal locations. For those of you not familiar with octal, it's probably a good time to start because that's all we use here at Cray Research is octal. Octal and binary. So if you're used to hex, save it for when you work on a disk drive or something. But anyway, so 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3 are going to be, through 2 to the 4th, are going to be bank address bits. So as we increment through our address, we say we want word 0, where our whole address is all zeros, 22 bits of zeros. We're going to go to bank 0, because these 5 bits are going to be equal to 0. Now, as we set 2 to the 0 to get the next word, we're going to go to bank 1. And we're going to increment all the way through all 32 banks, or 37 octal banks, until we get up here to 2 to the 5th and increment that. At which time, we're going to be incrementing now the internal address inside a chip on a module in bank 0. So we're going to go back to bank 0. If you see this picture in your mind, as you increment finally get all of these bits set and get a 1, 1, or 37 octal, if we add one more to it, they're all going to toggle all the way up, aren't they? And we're going to get a carry into 2 to the 5th position, set 2 to the 5th, and then we just went to the first address inside a 16K chip from address 0 to address 1. Now, any question on that? That's the bank addressing scheme. If you look over here at the chassis maps now, you'll notice there's a group of modules labeled throughout memory, and they're labeled in bank format. Bank 0, bank 1, 2, 3, 4, etc., all the way around memory. That's what I was talking about. So if you go to memory and you want to write or read a data word, you're going to go to bank 0 if your address was equal to 0. As you increment your address, you go from 0 to 1 to 2 to 3. Eventually, you'll go all the way through and get down here to bank 37. And then you'll go to the next internal address inside the chips of bank 0 and then go through the whole scheme again. So we said inside bank 0 there's got to be 72 chips, doesn't there, to hold that data word, because the data word is 72 bits long. And we've addressed now through all the banks. It's going to take us quite a while to get through all the locations inside that chip. Well, how many address bits do you need to address one of 16,000 locations? I'll cheat and look. Yeah, it's 2 to the 5th through 2 to the 18th is going to be our internal chip address. All right, so all of these bits, 2 to the 5th through 2 to the 18th is internal chip address. But wait a minute, we don't have enough storage locations yet to make 4 million words, do we? We need another 3 bits. 2 to the 19th, 2 to the 20th, and 2 to the 21st. Those are going to be chip selects on a particular module or inside the bank. So we have 8 different chips on this module after we go through the internal address. So let's see, how do I designate that? If we take and look just at bank 0, in other words, bank 0 is going to say I can handle all addresses that where the first 5 bits are 0. In other words, I have enough storage so I have enough chips for each data bit in bank 0. There are 8 chips, 8 16K chips for each data bit. So if I isolate in bank 0, remember bank 0 is 72 bits wide, isn't it? I told you it had to have 64 bits of data, 8 bits for check bits locations. We had to store that right along with the data word. So there's only 4 3ZV modules in bank 0. Well, take 4 and divide it into 72, you should get 18. Each 3ZV module has 18 bits of the data word on it. The module at location D8 happens to handle the lowest 18 bits, 2 to the 0 through 2 to the 17th. The next one up handles the next 18 bits, which is 2 to the 18th through 2 to the, I was never good at this, 35. Yeah, 2 to the 35. The next 18 bits are on D10, and that's 2 to the 36 through 2 to the 53rd. Whew. And the last module in bank 0, which is D11, handles 2 to the 54th through 2 to the 71st. And there's our 72-bit data word, all on 4 modules. Since each module handles 17 bits of the data word, and I just told you that for each data bit, there are 8 different chips to put that data bit in. How many memory chips do we have on one 3ZV? How many? 136? Let's see, we got 1 bit, 18 bits times 8. $144? Well, that's close enough. 136. Well, one of them cells has got, or one of them chips has got some bad cells in it. So. 144 chips. Well, remember we're talking about the 24. There's 144 memory chips on that module. Each of these memory modules has 144 memory chips on it, and it had to probably have some address chips and write enable and data and etc. also, right? Those modules are pretty compact as far as leftover space on them. In fact, they run also just a tad warm. Each module, if you also noticed when I was talking about these modules in bank 0, I went 8, 9, and 10, and 11. They're single modules, just one cold plate with a PC board on each side of the cold plate. Each ZV module is a single module. In other words, there's a PC board with modules. Hopefully, let's see, what's half of 144? 72 memory chips on each side. That one module draws 27 amps, roughly. we use a -5 voltage supply. So how many watts is that? 27 amps times, this is a bunch, huh? 150 watt module. All right, if you powered 30 XMPs up at once, I think the river would go backwards because the demand on NSP over here. Start turning the generators the opposite direction. Anyway, or at least it'd stop it. Okay, so I've told you then, I didn't make it real easy and straightforward, but I did tell you everything you need to know about memory to pull out one memory chip or one memory module and fix a bit on that module, didn't I? I told you use the address here to get it down to a bank. I also told you, I didn't write it down though, I will, is how to get inside a bank to find a particular data bit. Sure, now I got to go through. I should have wrote this down. I wouldn't have to go through this again. All right, here's one bank. I said the first module has got bits, the lowest numbered module in the bank. Remember that, 0 through 17 on it. Or 2 to 0 through 2 to 17. We'll just say 0 to 17. The next module up has got bits, what did I say, 18 to 35? The next one's got 36 to 53, and the next one's 54 to 71. All right. Well, no, given this information, this is, let's see, location. Let's see. We'll call this location n. This is n plus 1, n plus 2, n plus 3. In other words, the lowest number, chassis designator number, n plus 1, n plus 2, n plus 3. So for any given bank, that would give you a chassis designator now. Then let's see if we can figure this out. Let's say that we have an address. Well, they ran out of space on the board. Now, let's suppose that we had an address like this. In other words, it's address 1005. I've just appended the leading zeros on there to take up the bit positions. Given an address 1005, you should be able to using this information, first of all, to decode which bank it's in. Well, in other words, you take the lower 5 bits of this octal address or octal number I've given you, and you write it down in binary. A 5 is a 0, 1, 0, and then a 0, another 0, and then the rest of it here we'll just leave off. The lower 5 bits of this address are right here. Bank, overall bank address 5. Well, bank 5, we know where that is. We can go over here to our handy little chassis map and say, there it is right there. At P 12 through 15 is bank 5. If we had a failure at location 1005 and we dropped or picked 2 to the 14th, and if some error reporting scheme on the computer told us that information, we now know which module to go and pull out, don't we? Because we said it was bank 5, that get it down to 4 modules. Now all we got to do is say which one of those 4 modules is bit 2 to the 14th on. Well, we said the lower 18 bits, 0 through 17, are on the N location module. All right. In this case, since our numbers go from 12 through 15, N is going to be 12. And so the module at location P12 is the module that we want to get out of there, so the customer can run error-free with his memory. Any questions on that? Everybody see how I did that? So I took the lower 5 bits of the address, wrote them down in binary. I didn't have to do that, but if it had a different number other than zeros here, it might have been more confusing, I guess. I then rewrote it and said, well, I'll take this and write it as an octal, an octal number, a 5 octal, and this is a 0 octal. So bank 05 is the one that failed. All right? Now, all I did was take that bank 5 information and walked over to the chassis map and looked for bank 5 and said, oh, there it is, right here. Here's bank 5. And then which module amongst bank 5 handles bit 2 to the 14th or bit 14? And it was the lowest numbered module. But notice the lowest numbered module in the P chassis is the one closest to the top. It's a little tricky. When they numbered the chassis over here, they started at 0 and they went both ways. If you've worked at cray research for a while, they'll say, oh, that's nothing big, right? But if you haven't, you say, whoa, that's weird. Well, yeah, just the way it is. Any question on this? You want to do another example? I'll give you a little harder address this time. This one was for me to do, so I gave myself an easy one. Let's go over here and say,
here is videotape exercise number 1 for memory. The address equals 1540136 octo, and the failing bit equals 2 to the 42nd. What is the module location that handles bit 2 to the 42nd? This problem is also found in your course materials. Please stop the videotape and work out the problem in your guide. Restart the tape player when you're ready to go through the answer.
what I did is I'll take these lower 5 bits of this octal number, 76. Let me write them up here. 76. So that's a 111110, 76. The lower 5 bits of which are like this. And I said we've got a 6. And if I append a 0 on here, squeeze a 0 in there so that I have 3 digits to make an octal number, then I'll have a 36. All right, so bank 36. Bank 36 is in the I chassis at the top of it. Must be 55, 4, 3, and 2, huh? So we already know of the module location, the designator is I. Then we say which module holds bit 2 to the 42nd. And if we go here, 17, no, it's not between 0 and 17, or 18 to 35, but it is on this module, so it's n plus 2. N in this case was 52, n plus 2 is, indeed, I-54. All right, see how I did that? Any questions on it? All right. Now, if you'll notice, there's exactly 1, 2, 3, 4, 5, 6, 7, 22 bits of address given here. This 1 is a single bit all by itself, isn't it? In a 22-bit address scheme, that bit can only be a 1 or a 0, since it's a single bit. Now, using this same thing here, it says the upper 3 bits, 2 to the 21st, 2 to the 20th, and 2 to the 19th, tell us the chip select on that module, don't they? We can then take and look at these upper 3 bits, and we have a 1 and a 5. Let's see. So a 1, which is a single bit all by himself, and the 5. And look at the upper 3 of them and get a chip select. Chip select equals 6. In other words, 4-bit, what bit did I give you? 42. 4-bit 42 here was the 6th chip for bit 42 that failed in this case. All right? In other words, there's 8 chips total that'll hold bit 42 on that module. And this happens to be the 6th one on that module that failed. Now, if we knew how to go from a number here to which physical chip it was on a module, we could pull the module out. We already know which one it is. It's the I-54 3ZV module. Since we don't know how to change the chip yet, we can put the spare module back in and get the customer back up running, and we can take this module over to a repair station. At some point during your time here at Cray Research, you'll be trained how to take that chip out and replace it with a good one. And now you've just fixed 90% of the problems in the field are memory problems. See, so you already know how to fix 90% of the problems you're going to have. So those are 10% that are real killers. Any questions on the addressing then and the bank divisions? In addition to determining the bank address, excuse me, the way that we did, there's another way, and the reason I'm going to show you this is because this is the way the machine actually does it inside the computer. What the machine is going to do is, first of all, it's going to take the lower 2 bits off of the bank address and decipher them into a section address. What that says then, there are 4 different sections of the machine, isn't there? 0 through 3. And if I go over here to the chassis map, the sections are, section 0 is the D chassis. Section 1 is the P chassis, 2 is I, and 3 is the U chassis. So there are 3 separate sections of memory. Each of those sections has 8 banks in it. So there's 8 banks and 4 sections. 8 times 4 is 32 banks overall. Now you should be able to get the same information either way of these, either of the 2 methods used here. So we have a section address and then a bank within a section. Which equals an overall bank address. An overall bank address can be gotten from the section and the bank in a section. So if we use that format on our 36 that we had here, we said we could take this and say it's section 2. Right? Any question on that? We just strip off the lower 2 bits, 2 to the 0, 2 to the 1, and say it's a 2. In binary, octal equivalent is a 2 anyway. We go over here to section 2, it goes D chassis section 0, 0, 1, 2. And indeed, bank 36 is in section 2, isn't it? Now, if we look at the upper 3 bits of the bank address here, we've got all 3 1s, which is the equivalent of a 7 in octal. Well, if we start at the lowest numbered bank in this section, section 2, and call him bank 0, and then go 0, 1, 2, 3, 4, 5, 6, 7. Bank 7 in section 2 is overall bank 36. Like I said, that's the way the machine does it. In other words, each section, there's a control module that gets turned on and says, I want to talk to bank 7 in section 2. So you should be able to do it either of the 2 formats to establish which bank you're talking to. Hopefully you'll get the same answer both ways. If you don't, you did something wrong, one of the 2. That made sense. But anyway, any question on that? So there's 4 sections of memory. The lower 2 bits of address, 2 to the 0, 2 to the 1 of the memory address point out which section. The next 3 bits, 2 to the 2 through 2 to the 4, point out the bank within a section. Overall, 2 to the 0 through 2 to the 4 can be decoded to point to a bank in the machine, and you can go from section and bank in a section also and get the same answer. Now, You can also take the upper 3 bits, 2 to the 19th, 2 to the 20th, and 2 to the 21st, and decode from that information the chip select on a module. Once given the bank information, knowing the data bit within the bank that failed, you can decode a module. Using the upper 3 bits, you can get a chip select on a module that's active, and you can get down to a chip. This internal address, you really don't care about, do you? There's no way yet that they've discovered that you can go inside a chip and fix that. I suppose you can get out your laser saw and cut it open and then get in there and weld a little cell or something back together. I don't know. But they haven't figured it out yet, but they're probably working on it right now. Think of the money they'd save in chips if you could fix them, huh? Anyway, any questions on how to do this then? Decode an address and a data bit position down to a bank on a module. Want to do another example? Okay, good. I like to do examples. Let's say this will be all right, given an address of 1501, bit position 61, what module? Let's see, we'll take the lower 5 bits of the address. A 1, octal 1 is a 001, and then a 0. The lower 5 bits of which are, well, remember now there's 2 ways to do this. We can say section 1, bank 0. Section 1, section 0, 1, bank 0, which is the first bank in section 1, which is the ZV modules from location 8, 9, 10, and 11. Well, at least we got the right group of 4. So 8, 9, 10, or 11, at least you're in the right bank. You're only, if you got the wrong one, you're only 3 swaps away from getting the right one. Maximum. Now, we said take 2 to the 61st as your data bit. We said the lowest numbered bank in that group of 4 modules, or lowest numbered module in that group of 4, is going to have bits 0 through 17. So location P8 is got 0 through 17, 9 has got the next 18, 10 the next 18, and 11's got the upper 18, wherein lies 2 to the 61st. P11 is the correct answer. Now I can see how some people got P8 because they went to the lowest physical position, not the lowest numbered. I got some of you there. All right. So P11 is right. Now, what about the chip select? Oh, wait a minute. I didn't give you enough bits here, did I? Well, being lazy just like most everybody else, most I say. I didn't say you were lazy, I just said most people generally are lazy. I'm really lazy. But anyway, I don't like to write down any more bits than I have to, so I only put down the lower 4 bits of the address. Everything above that was all zeros. Knowing that now, you can say, oh, well, why didn't you say that? Now I know 2 to the 21st, 2 to the 20th, and 2 to the 19th were equal to all 3 zeros, aren't they? Therefore, chip select 0 was the one that was active on that module. All right? And so I'm going to do that all the time now, so I won't have to write all them extra zeros in there. That way I can give you an address that's less than 22 bits. I don't even have to count them. I'll just write something down. Told you I was lazy. But anyway, any question on how to do that? Does everybody have the idea now? All right. Well, now we'll go and talk about something else for a little bit here. We talked about the addressing of memory. I told you already the data word is 64 bits. I said on the way into memory, what we're going to do with those 64 bits of data is we're going to look at them in such a way as to create 8 check bits and write them right along with bit 2 to the 61 and the rest of the data word, 2 to the 0 through 2 to the 63. There's going to be 8 data bits appended onto there. They're always going to be stored in which module of the bank? The 8 check bits. Any particular modules? The upper one, the highest physical numbered module within a bank is going to have the 8 check bits on it, because those are bits 2 to the 64 through 2 to the 71st. So if you're having a problem with your check bits in a particular bank, what's the easiest solution to get a problem fixed? Is take the check bits and move them down one module. And now it's just a data bit. You can correct data bits and you can look at the information on a data module much easier than you can check bits. In other words, the error correction and reporting is such it will report out a chip in error if it's in the data word. But if it's in the check bit, it just tells you it was a correctable error and everything's fine, but there's something wrong somewhere, but we aren't going to tell you where. So if you move it down one, it'll say, oh, it's bit 2 to the whatever, and that's one that failed. All right. The way we look at them, and in your hardware reference manual, or let's see, where else is this? In memory, in the memory section, which is section 2 of volume 2, page 2-3, there's a picture like I'm going to put a transparency up here. So there's also a picture like this in the hardware reference manual where they explain it. And what this is, the data word 2 to the 0 over here through 2 to the 63rd broken down into 8-bit bytes. Each of these bytes got a bunch of little X's and dashes underneath it. What this is this is the method that we're going to do error correction on the cray 1S or the XMP or XMP48 or any other computer at Cray Research. What we do is we take and look at a particular data bit here, and for that data bit or group of data bits, we check certain bit positions to create check bit 0. Check bit 0, or bit 2 to the 64th here, for example, we look at all of the odd bits 1 through 31. In other words, we just check it physically to see if it's set or not set. We then look at all of the bits 32 through 55 and see if it's set or not set. Once we've done that, we now know if we have odd or even parity. If we have an odd number of bits, then we set check bit 0. In other words, we have an even parity machine. If we have an even number of bits, then we don't set check bit 0 or 2 to the 64th. And then we do that for the rest of the check byte, all 8 bits, checking a different group of data bits every time. All right? For check bit 1, we said we checked all the odd bits 1 through 31, and then all of the bits through 55, and then none of 56 to 63. For check bit 1, however, we check bits 2 and 3, 6 and 7, 10 and 11, 14, 15, 18, 19, etc. Every place there's an X here is a place we check to see if it's set or not set. We check all of byte 4, all of byte 5, none of byte 6, and all of byte 7. Once we've checked them all, we said, okay, now we have an odd or even number. We'll have one or the other, and then we'll set to the 56th accordingly. Any questions so far? All we're doing is looking for even parity among this group of bits. Every place there's an X for check bit 7 or 6 or 5 or 4 or 3, that's one of the bit positions we check. All right? Well, let's say then, for example, that when we check this entire data word, whatever the data word was, this is the check pattern that we created. That didn't work out right. All right. This is the bit position 2 to the 64th through 2 to the 71st, check bit 0 through 7, or 8-bit byte. And I'm just going to assign values here. All right. What this says now, this is our old check bit. I'm going to call it the old check bit rather than anything else. Now, what this says, when we created check bit 0 or bit 2 to the 64th, we looked at all of the even or all of the odd bits, 1 to 31, all of the bits, 32 to 55, and we said there's an even number of bits set, so there's no need to set check bit 0. And so we didn't. We had it as 0. Then we go through each bit position group here and look at all them data bits. For check bit 1, we looked at all those bits, 2, 3, 6, 7, 10, 11, 14, 15, 18, 19, 30, 31, etc. All the way, all of byte 4, 5, none of 6, all of 7. And there was an odd number of bits set. So we made it even by setting the parity bit. We continued on through the rest of the data word. All right. Now, we take these 8 bits, we append them onto the end of the data word, 2 to the 64th through 2 to the 71st. We write them into memory at some address. Once we write them into memory, they're hopefully will stay there and not change. But what happens if they change or one of the memory bits change? Let's say, for example, that one of the data bits changed. Pick a bit. Any data bit.
3.
Data bit 3 changed. Now, I didn't say whether it was set or not set. I just said it changed, right? Well, if 2 to the 3rd changed, when we create check bit 0 again on the read now, we're going to take the same data word that we wrote in there, except for bit 3 is changed now, and we're going to recreate this check pattern. We're going to call that the new check pattern, because it's newer than the other one. All right. Well, if bit 3 is now not set, let's say we dropped it. Let's say it's not set. Are we going to have an even number of bits when we look at all the odd bits, 1 through 31 and all of them through 55? Yeah, we will have an odd pattern now. Before, we had an even number of bits, didn't we? It was a trick question, I guess, unintentional. But anyway, it's different, isn't it? So that means rather than not setting a check bit, now we'll set it, won't we? All right. Let's look at check bit 1 then here. Well, if we look at the second group of X's down, we look at check bit 3. We said before there was an odd number of bits. We dropped 3 out of there. Now we're going to have an even number, aren't we? If it's an even number, that means we don't have to set check bit 1. All right. See that? Any questions so far? All we're doing is saying check bit 3 is one, or bit 3 is one of the bits we're looking at to see if we have an odd or an even number of bits. And whichever we had with 3 gone, we're going to have the opposite, aren't we? Follow me? If 3 was set and now it's gone, we had an odd number of bits before, now we're going to have an even number. And so there's no need to set check bit 1. What about the next check bit down? Check bit 2. Here, the second 1, 2, 3rd group of X's down. Do we look at check bit 3, or bit 3 here, data bit 3? No, we don't even look at it. So it can't affect the state that we checked here before, can it? before we had an odd number of bits. We didn't look at bit 3 didn't come into play here, so we're still going to have an odd number of bits, aren't we? So that's going to be set. Check bit 3, which is the fourth group down. 1, 2, 3, 4, right here. How about there? Is going to change or stay the same? Stay the same. So we're still going to have a 0 there. We had an even number of bits before. If you take away 3, it doesn't change whether we had an even number of bits because we didn't look at that one for that group. What about the next one? Change. Next. Next. Last. We don't even check it for the last, for check bit 7, do we? We don't look at any bit in byte 0. So that was a 1 before, it's going to be a 1 now. All right. Now, we've got our old check bit and our new check bit. Now what we're going to do is we're going to take this, or old check byte, new check byte, we're going to take these, we're going to run them through an exclusive OR circuit. And what that's going to do is every place there's a difference, it's going to set a bit down here. Let me change color. A 1 and a 1 in an exclusive OR circuit is going to make a 1. A 1 and a 1. Here we have two 1s. Since there's no change, it's a 0. No change, 0. Change, 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 0. What we're going to do with this conclusion we came to here, we're going to call it a syndrome. A syndrome, if you look it up in the Funk and Wagnalls, it'll say it's a symptom of something or other. What this is going to point to is it's going to point to a particular data bit, hopefully bit 3. But anyway, we should be able to take this group of 8 bits and decode out of that group of 8 bits a single data bit. And the way we do that is like this. We first of all count off 4 bits. 1, 2, 3, 4. Divide it in half. Now we examine these two halves of the syndrome character. And we say, does half of it have 3 1s and a 0? Yeah, right here. There's 3 adjacent 1s and a 0 bit. In this half of the data word, then, that bit is the byte pointer. The byte pointer is counted exactly opposite of the check bits. So that's byte 0, 1, 2, 3, 4, 5, 6, and 7. 0, 1, 2, 3, 4, 5, 6, and 7. So our byte pointer is pointing to us. This 0 says byte 0 failed. Well, bit 3 is in byte 0, isn't it? So far, so good. Now, we take the other half of the syndrome character that we haven't touched yet. We take the least 3 significant bits and put them through a 1 of 8 binary, 3-bit binary to 1 of 8 decoder. And we should come up with a 3, an octal after that, right? 0, 1, 1 is equal to a 3. So it's bit 3 in byte, in this case, byte 0. Bit 3 in byte 0 is bit 3 overall, isn't it? We go byte 0, 0, 1, 2, 3. There it is. So this syndrome character says bit 3 changed. Now, all we have to do on the output of the module that does this checking, he says if bit 3 changed, that means whatever it was before is the opposite of what it is now. So all I have to do on the way out the door is just flip it over. If it was a 0 before and it's a 1 now, I'll just set it to a 0. Or if it was a 1 and we dropped it, I'll just reset it to a 1 and it's the right state again, isn't it? So this is how we do error correction on the XMP. We create a check bit, write it into memory along with the data word. On the way out of memory, recreate the check bit or do the checking go through the checking network again, looking for even parity. We then compare the old and the new check bits or check patterns, create a syndrome character, we decode this syndrome character to give us a bit within a byte. From that information, we know then which data bit failed. But there's some other rules that apply here also that solve any of the problems that you can think of right now offhand. And that is at 77. You also have to have an odd number of bits overall before it's a correctable error anyway. All right. So there's also a network that's checking and saying, well, do I have an odd number of one set? Well, yeah, I do. I have 1, 2, 3, 4, 5 of them. It's a correctable error. I then look for this and say, yeah, it's a single bit correctable error. And then I say, yep, it's byte 0, bit 3 within byte 0. Three ones and an adjacent 0 and half of the syndrome character is what you're looking for, yeah. That's a real easy circuit to make. All you got to do is invert. For byte 0, you invert this and 3 ones and AND them together in a big AND gate, right? Say, yep, this byte's an error. Or for whichever bit you're looking, or whichever byte you're looking at. So half of the data, or half of the syndrome character is always going to have 3 one-bits set and a 0 somewhere in that field.
And that's your byte.
And that's the byte pointer then.
So losing the right side of the field, it would just be byte 7.
Byte 4 through 7, right. Exactly. If the byte pointer moved over to this side, then we've got bytes 4 through 7 that failed. And then we use the other half of the syndrome character to predict the bit within the byte. Okay? I'll show you an example of that. Okay. Here's a syndrome character. I've written it out in binary. This is check bit 0 through 7. I divide it in half. Now I examine this and say half of the check bit has got 3 ones and a 0 in it, doesn't it? And it's on this half. The byte pointer then is over here. There's the byte pointer. Which byte failed? You start here at check bit 7. You go 0, 1, 2, 3, 4, 5, 6. Byte 6. The least 3 significant bits of the other half of the word are going to tell you the bit within the byte then. So bit 6 of byte 6, in this case, failed. Bit 6 of byte 6 is, well, here's byte 6. We go 0, 1, 2, 3, 4, 5, 6. Bit 54 failed. Or 6 times 8 is 48 plus 6 is 54. Did I do that right? Yeah, worked. All right. So, now I didn't say which data pattern caused this or what happened. All I say is given this syndrome character, you should be able to predict which byte and which bit within the byte failed. Once you know the bit within the byte, or the actual bit that failed, if you know an address, you can tell me which module it was on, can't you? Everybody's nodding their head in agreement. Well, let's see if you can.
Here is videotape exercise number 2 for memory. The syndrome character equals 307 octal, or 1100011 to the base 2. Address 1425 octal is failing. What is the memory module location that handles this address and bit failure? Please stop the videotape and work out the problem in your guide. Restart the tape player when you're ready to go through the answer.
All right. The answer is P46. Everybody get that? Now, the way you do it is, first of all, this is the byte pointer. Remember, you count that backwards from the actual check bit position. So we go 0, 1, 2, 3, 4. So it's byte 4. And the least 3 significant bits, which are a 1, 0, 0, are the bit within the byte pointers. And so this is bit 4. Bit 4, byte 4. Now, there's 8 bits in every byte, so 8 times the byte is, or 8 times 4 is 32, plus 4 is 36. Or I can come up here to byte 4 and say this is bit 0, 1, 2, 3, 4. Got to remember to start counting at 0 though. All right, so bit 36 is the one that failed. The address gives us the bank position. Now, let's see if I can find some spare space here to write this out. We've got the least 2 significant bits of the address are 25. So 0, 1, 0. All right. Now, first of all, we'll use the bank and section format. We'll say it's section 1, bank 5. Section 1 is right here. Section 0, 1, bank 5. 0, 1, 2, 3, 4, 5. Get bank 25 overall. That's an octal number, however. If you'll notice, which I forgot to tell you, and which some of you found out the hard way, the banks are numbered both in decimal and in octal. So, come down here, there's 2 bank 25s, one at location 44 through 47 and another one at 48 through 51. Well, the first number is the decimal number and the second number is the octal number. And we wanted octal bank 25. All right? Thank you for pointing that out to me. So the actual location then is the third module up, because there's 18 bits on each module. The first module's got 0 through 17. That's the one at P44. The next one's got 18 to 35. That's P45. And the next one up, P46, has bit 36 on it. So that's our module location. Any question on how to do that then? If you look in, let's see, where are the rules here? On page 2-2, it says the matrix is describing, I can't read upside down, that's what it says. Designed so that a syndrome bits of all zeros say there's no error. Well, if you do an exclusive OR of 2 numbers that are equal, you should get all zeros. If you get well, the rules are there, you can read them, I guess. Yes.
I'd like to go back to my same question. What happened from the design point of view is part of yourself, because you have to have the arc parity for the syndrome code.
Okay. In other words, if you have a syndrome of 77, what is that equal to?
What happened? Something wrong, something failed, so that
The rule, which rule is that? It says, which rule is it? Number 3. It says that if more than one of the syndrome bits is a 1, but there's an even number, then you have a double bit error. All right. So in other words, it's detected the fact that you've had 2 bits in error, and automatically the machine says, "Oh, that's a double bit error. I can't do anything about it, so I just give up and say, oh, that's it. Too many." The software pukes you out onto the floor, your program. Yeah. And in fact, if you get a multiple bit error, it will sometimes look like a single bit error. All right. But understand, to get a multiple or a double bit error, it has to be more than 1 bit failing inside a bank. That's another good reason for interleaving. Now you've got it down to a bank. You know which bank it is that's getting the double bit error. You're 4 modules away from getting the module out that caused it. There's only 4 modules in that bank. Nothing else. You can swap them one by one into a different bank. You know the address, so you know which bank is getting the double bit. So it's 1 of 4. Shouldn't take you more than 4 swaps to get it. If it does, you have to go to, I don't know, try again, I guess. It's always the last one you swap. Right? Yeah. Why keep swapping if you found it? All right. So, any questions on error correction. Well, this handy-dandy little chart of x's here will tell you more information than just bytes and which bytes are within a bit and what bits within that byte we check for a specific check bit. And that is, let's take our check pad or syndrome character here, where we had a 1 1 0 0 0 1 1, and let's see if it can't help us decode which bit's in error. Well, if I take, see, there used to be some colored pens suitable for writing on the side here. Here we go. If I take this and turn it this way, and now I'm going to look for a 1 1 1 0 0 0 1 1 in there. That's the only pattern right here. Bit 36 is the only one that's going to report or could possibly report that specific pattern. So we've got a 1 1 0 0 0 1 1. Bit 36. It's the only one that can separate and distinct syndrome character for every possible bit pattern, in other words. Why is that? Well, we checked the syndrome or the check bit, old and new check bit patterns are going to be different in these three positions, aren't they? And in these two positions, but they aren't going to care about those, or they won't change for those because you didn't even check them. Also notice, when it's turned this way, here's our byte pointer in the syndrome character, isn't it? We didn't check any bits in byte 0 or byte 1, 2, 3, 4. Now we switch halves of the word here. And also, if we use byte 0 as an example, there's our half. Notice how the least three significant bits here just do a count. 0, 1, 2, 3, 4, 5, 6, 7. All right? So the chart of x's, the bits that we check, influences the syndrome character we get out, of course. It has to. All right, so inside the machine, this is how we do error correction. No magic at all. Not even any mirrors. Pretty straightforward. Any questions on it?
Is there a module that's responsible for check bit or that?
Yes. There, on the data pattern on the way in, there's a set of modules that generate the check pattern on the way in. On the way out, on a read, you take the data word and the old check bit pattern, and you create the new one and then compare them to create the syndromes, and then it's a specific set of modules. It takes more than one. In fact, it's two modules that do that error correction on the way out. So that's their function, and it takes 2 clock periods in the machine to do this. So it takes, let's see, 19 nanoseconds to correct 72 bits, or 64 bits, I mean. Well, we've been doing most of our talking thus far about memory. In other words, in the center of this block picture. And all I've talked about is addressing and error correction. I haven't even really got into, I guess we talked a little bit about the layout, but it's been only in these 2 center columns. No, 2 outside columns. Here and here. The center 4 columns we haven't even talked about. The majority of the machine. Well, the actual memory modules are the 3 ZVs. We already knew that. They're arranged in banks. Now, there are some other modules here in the memory area of the machine. There's some ZZ modules, 3 ZZs. There's a 3ZX, or 2 of them in each section. And there's some 3ZY modules. Those modules are, along with the ZVs, are the memory modules themselves. Anything that starts with a Z, you'll notice, or the 3Z, is something to do with memory. Well, as you go into the center 4 columns, you'll notice there's some modules inside here that say 3ZE's error correction on them. Well, those are the modules assigned to do the error correction for that section. So there's 4 3ZE's there that do error correction on section 0's data word. But all we've done is talk about memory being arranged in banks. It's 4 million words in size. It's got 22 bits of address because that's how many you needed for 4 million words. There are some other things you need to know about memory. One of those things is that there are ports in memory. Now, memory ports are kind of a, I guess, a concept. And these ports are shown here in that there's ways in and out of memory to the CPU. And they're shown by these arrows. So it says it looks like there's a path here that goes between memory, or from memory to the vector registers. And it looks like there's two of them that go from memory to the vector registers. And there's one that goes the other way. And it shows I/O having a path into memory. And it shows these registers, it says scalar registers, S and T's, it shows them on their way in and out of memory. It also shows the A's and B's in and out of memory. And it shows there's another way out here down into the instruction buffers. If we lump all those different paths together, we're going to call them ports. And ports, all they are is a way to get data into or out of memory. Each CPU has 4 ports. In other words, you can do 4 separate and distinct things from one CPU into or out of memory all simultaneously. What that means is you can read a word out of memory and put it in a vector register. At the same time, you read a different word out of memory and put it in a vector register, hopefully a different vector register. And at the same time, you can write a word from an even yet different vector register into memory, hopefully at a different address. That's 3. Right? We did 2 reads and 1 write. And at the same time, you can be doing I/O activity in memory, either read or write. So I said there were 4 ports from each CPU. Four ports, 2 read, 1 write, and 1 I/O. Now, those reads, if you'll notice up here, there's a lot more than just 4 lines going in and out of memory, aren't there? So we're going to have to share these ports somewhat. And we're going to have to give them a name so we can keep track of them. Let's call them port A. That's going to be one of our first 2 ports. It's a read port. Or B register. So with port A, we can either read a vector, do a read to a vector register, or a read to a B register. We're reading memory, we're transferring the data either to a vector or to a B register. Port B, then, is going to be our vector, our second vector read port, or T-register read. In other words, once again, we're reading memory, transferring the data that was in memory out to either a vector register or a T-register. Well, there's our 2 read ports. Port C, then, is going to have to be the write. So our write port is for B, T, or V. So B or T or V. Any one of those, we're taking the data from a B register, a T register, or a V register and transferring it into memory. It's a write operation. Or A or S, Also, there's a little trick on ANS, and I'll have to tell you about that. All of the references I've been talking about, vectors, B's, or vectors and T's, are block transfers. In other words, it's possible that you're doing more than one word at a time, or sequentially. A vector register, for example, you could transfer 100 octal words of data from memory to a vector register, or the other way. Or 64 words, one right after another. Sequential words, you can't do 64 at a time yet, but you can do one right after another sequentially. The same way with the B or the T registers. They're block transfers. In other words, there's a block of data out there that you want to get out of memory and put in a T register or a B register or a V register. Or the other way, you want to take a block of B, T, or V register and send it out to memory, 64 words at a time if you want, up to. However, the ANS registers are single word transfers. In other words, you do one read or one write. And when they were designing the computer, they said, that's pretty inefficient, isn't it? One word at a time, when you could use B registers and transfer a whole chunk at a time. So what we're going to do is we're going to put them as the lowest priority. And we're going to have them wait until you aren't doing any of these A, B, or C references, block references, and then we'll let you do an A or S read or write. When you do that A or S read or write, the address for that A or S read or write uses port C's path. But the data comes back either, if it's a read, comes back either port A or port B, depending on whether it's A or S. More on that later. Don't worry about it for now. 3 ports, A, B, C. Read, 2 reads, 1 write. A's are different. A's and S's are different. Just remember that. Now, there's one port we didn't have to talk about yet, right? Can't talk today. I'm trying out a new tongue. And that is port I/O, of course. And what that's used for is I/O references. Now, there's our 4 ports. A, B, C, and I/O. So that means at any one time in memory, we could have 2 vector reads, 1 vector write, and some I/O activity going on in memory. And that's just from one CPU. That's just from this guy over here, CPU 0. CPU 1 could be doing the same thing. Now, there's a possibility that those addresses might want all the same addresses at the same time, isn't there? Anything's possible. And of course, it'll always happen if it's bad. And it is, so it'll happen. So there's going to be some conflicts in memory. If you have all these different paths and ways to get data in and out of memory, you're bound to have some data hitting heads. So they said, we'll have to solve these conflicts somehow. But first of all, let's define the conflicts. Well, let's see. Let's think about it. What type of conflicts could we have?
Bank busy.
Bank busy conflicts. Long time ago, about 1 o'clock or so, I told you that the access time on these memory chips was 35 nanoseconds, which figures out to be just about 4 clock periods. So if I go to bank 0 and ask it for a data word, I can't use bank 0 again for 4 clock periods. Well, if you got all these different ways to get in and out of memory, somebody's bound to say, I want to use bank 0 before that 4 clock period time is ended. And that's a bank conflict. Somebody's going to have to solve this conflict for us. How long is a bank conflict then? Always 4 clock periods?
Depends on when you want.
Depends on when you want it, isn't it? And is it 4 clock periods? Well, if I've just used bank 0 and I said you can't use it for 3 days, how long is the conflict? 3 days, right? It means totally it took me 4 days to get my money out of bank 0. It's a little analogy. Whatever. Anyway, the bank conflicts are 1, 2, or 3 clock periods. CPS is the abbreviation for clock periods. from this day forward. I always get a lot of hassle from different people about the way I abbreviate things. I figure if I train enough people, eventually everybody in the company will think like I do. So, a bank conflict. It says somebody else already used this bank. You can't use it for another 1, 2, or 3 clocks. It depends on how long ago they were here. All right? Any question on that? Well, before we can describe the other kind of conflicts, well, no, I guess there is one more you can tell me about. What else is there? Go ahead, Tom. But there is. What about the two CPUs? What if both CPUs want to use bank 0 at the same time? Well, the reason only one of these ABC or I/O ports from CPU 0 can access bank 0 at any one time, there's a reason that they can do that, and that is you can only issue one instruction per clock period. And so if you issue an instruction, it could be a port A or B or C or I/O type instruction, but that's the only time you can have, in other words, the only kind of conflicts you can have within a CPU are either the bank conflict or that one that Tom mentioned, the section conflict. But there's nothing that says both CPUs couldn't want to use bank 0 at the very same time. That's called a CPU conflict. Also known by some other people as a simultaneous bank. Simultaneous. But I figure why give it this big, enormous word I can't spell name when I can call it CPU conflicts, which is what it is. It's two CPUs want to use the same bank at the very same time, or CPU bank conflict, I guess. They both want to use bank 0, and you say, wait, somebody's got to wait. The other one can get it, but somebody is going to have to wait. What did I just tell you? I told you how long a simultaneous bank or CPU conflict is, didn't I? How long would it last? Just one clock period, right. Now, the next clock period, if somebody wants to use bank 0, or the other CPU, whoever lost the fight, wants to use bank 0, he'll have to wait bank conflict time, won't he? All right. Now, the other one that Tom was talking about is the section conflict. And the section conflict is where we conflict in these ZE modules. We can only get one data word out of section 0 through the ZEs at a time. All right? Since I've got 4 ports, there's a possibility of 4 different words wanting to come out of section 0 all at the same time, isn't there? And that's a section conflict. There's only one set of ZEs that do the error correction. It says, hey, it takes us 2 clock periods to do this. Give us a break. So we do have a section conflict. It says you can only bring out one word at a time to any particular port in that CPU from section 0. All right? So if port A and B both want 2 different banks in section 0, that's a section conflict. That takes 1 clock period to resolve, or that is a 1 clock period conflict. So we just say, one of you 2 gets to go first, the other one's got to wait 1 clock, and then he can go. Now, if you think about it, normally accesses are sequential, aren't they? We go to bank 0, then bank 1, then 2, then 3, then 4, etc. If we have a conflict for bank 0 and 4 at the same time, we'll say somebody waits, the other one goes, and next clock period there's no more conflict. It's resolved itself from then that period on, hasn't it? This guy says, I want 4 and I want 0, 2 different ports. If 0 goes first, next clock he's at 1, this one's at 4. And then we go 2 and 5, etc. It's resolved now until the reference is complete. All right, section. One CP. All right, so there's 3 types of conflicts. Bank conflict, CPU bank conflict, and section conflict. The bank conflict could be 1, 2, or 3 clocks. All the rest are just a 1 clock period conflict. In the XMP, what we're going to do is we're going to fully segment the entire machine. And what segmentation means is I'm going to use an adder, for example, here. If we wanted to add two numbers together, we would have our operands. If we bring both of our operands into this adder and then add them together, it's going to take a certain number of clock periods before we get a result out. Let's say this one's 3 clock periods. Well, 2 clock periods. What the heck. All right? If it takes 2 clock periods before we get our result out here, that means in some computers that you can't send anything to the adder except for every 2 clock periods. Now, when Seymour originally designed the Cray 1S, he said, that's not good enough for me. I'm going to fully segment it inside this adder. In other words, you can send me 2 sets of operands. I will take those operands and I'll do the partial add up until right here. At that point, I've got part of the add operation done. Not all of it, just some of it. I'm then, the next clock period, I'm going to move this partial add out to here. And there I've got most of the add done, but not quite finished yet. And then I'm going to take and move the add out of the adder, and I'll finish the add so that when I get out here, I'm completely finished with this add operation. What I do at the interim is I'm going to put in latches inside this adder the partial results. So I'm going to have 2 sets of latches here. And I'm going to put partial results here, and here they're almost finished results, but not quite. And so that means that when I have my first set of partial results at this time, you can send me another set of operands. Because by the time they get to here, I'll be already advanced to here, won't I? And by the time the second set gets here, the third set will be out there in the result register, or the first set. And at the same time, you can send some more. The entire machine is built like this, fully segmented. So every 9.5 nanoseconds in a set of latches is the information. Memory, for example. Every clock period, the address on its way to memory is in a set of latches somewhere, until it finally gets to the memory chip, and then it stays in a set of latches for 4 clock periods. And the data that comes out of memory, every clock period goes from one set of latches to another set of latches, to another. So that's why we can keep sending information, addresses to memory every clock period. As long as we have at least 1 clock period between the 2 addresses, everything will just roll right down through the machine. And that's the full segmentation. All the functional units, memory, everything, the control, everything in the entire machine is fully segmented like that, so that every clock period you can predict if it left here, next clock period is going to be there, and this operation was done in between. Okay? Now, we started talking at the end of the day yesterday about some other things in memory. One of those things was, we said there's how many ports in memory? 4 ports. What are they? A, B, C, and I/O. So what's port A used for? It's a read port, first of all, for vectors. Anything else? What about port B then? Must be write port, huh? Oh, read port. Oh, okay. C must be the right port then. And A and S also uses this port. We said that something about A and S registers that are different. We said they're one-word transfers. And so there's some things that you have to do with the A and S registers. One of the things the A and S registers, before you can issue an instruction that reads or writes memory to an A or S register, and that one thing is that none of these ports can be busy, A, B, C. They all have to be quiet. In other words, there's no vector or B reads or writes going on at this time, and then we'll let scalar go, or the A or the S registers go. The reason for that, they said, is it's a very inefficient way of getting data out of memory, so we'll make it wait for last. Once it does issue, its address is going to use port C. If it's a read, its data is going to use whichever associated port the data is going to. The B registers are associated with the A registers, so the data for a A register read is going to come out of port A. The T registers are associated with S registers, so that if it's an S register read, the data will come out port B then. And also, they're going to hold off any block references after this instruction issues for 3 clock periods. The reason for that is we don't have to worry about it having any bank conflicts then. In other words, if we issue an A register read, we're going to be using this port for the data, but we're also going to be referencing some bank in memory, aren't we? When we reference that bank, we don't want the next clock period somebody else coming in and trying to use that bank. It's going to be busy for 3 clocks anyway, so we might as well just hold them out for an additional 3 clocks and then let them go, and now we don't have to worry about them having a bank conflict right off the bank. All right? Well, that must mean then, when an instruction that uses vectors or B's or vectors or T's or writes, when that instruction issues, it must reserve that port, huh? Remember, we said a vector operation, you could be transferring a whole block of data, maybe 64 words to max. Maybe less, but it could be 64. For that case, then, if we're doing a vector read and we're using port A, we're going to be using port A for 64 transfers, aren't we? That's going to take 64 clock periods. Not counting any startup time there might be, but it's going to, as soon as we get our first word into the register or into using port A, right behind it's going to be another 63, 1 clock period apart. Remember, everything's segmented? And so it's all going to start flowing out all together. That means for 64 clock periods, we'd be using port A. The same way with port B or C or any of them. Block transfers to B or T registers are the same also. They could also have a word length of 64. And we'll be using that path, which is what we're talking about here when we say port. In this case, for data out for that many clock periods. Now, you notice we use both port for a vector read. We use both ports B and A. There is a priority scheme here. In other words, when a vector instruction wants to do its read, first it's going to use port B. Only if port B is not available will it use port A. All right, that means if you issue or you do 2 vector reads, one right after another, the first one will use port B, the second one then will use port A because B is no longer available. All right? Now, we said there's 4 ports into memory. Does that mean there's 2 in CPU 1 and 2 in CPU 0?
4 ports per CPU.
That's right. 4 ports per CPU. The only time there's only 4 ports is if you have a 1 processor. Exactly. With all these different paths into memory, aren't there some problems that could possibly exist? We already talked about one of them. We said bank conflicts, right? What causes a bank conflict? Why is there such a thing as a bank conflict?
Chip access time.
The chip access time. So there's 3 types of conflicts, I said. The first one is bank conflict. How long does a bank conflict last?
1 to 3.
1 to 3 clock periods. All right. What's another type of conflict, Ginny?
CPU conflict.
CPU conflict. Which is a simultaneous. A CPU conflict or a simultaneous bank conflict. That means both CPUs, any port it could be, but both CPUs want to use the same bank at the same time. How long did we say that would last? Well, we have to have some means of resolving this conflict, don't we? How do you think we do it? What would be a good way to do it, I guess? Any ideas? Give one priority. We could say CPU 0 always goes first. That'd be one way to do it. That wouldn't be fair, though. Let's do it fair. We'll switch back and forth. Is there any number that might be a good number if we're going to switch back and forth to use? Or 1 to switch back and forth? Exactly, 4 clock periods. So what we're going to do is we got a little counter somewhere in the machine that assigns CPU priority. For 4 clock periods, CPU 0's got priority. Anytime you have a simultaneous conflict, CPU 0 wins. The next 4 clock periods after that, CPU 1 has priority. Now, if you think about it, the bank conflict time is a good number to use there. All right? It's also the number of sections. So if you were doing a bank conflict, if you had a bank conflict, this guy is waiting, let's say he's waiting on bank 0. Both CPU 1 and 0 both want to use bank 0 at the same time. CPU 0 wins. We're going to come around and wait 4 clock periods before CPU 1 can go in and get bank 0 again anyway. Well, what if it just so happened that CPU 0 wanted to use bank 0 again? Maybe his count was such that he only wanted to reference words out of bank 0, and he was waiting on a bank conflict also. Now they're both trying to get bank 0 again. Well, CPU 0 won last time. CPU 1 is going to win this time because of that 4 clock period time. So that way you're trading off every time, every other time. If they're both maybe getting 100 words out of bank 0 for some reason, 100 octal words, you'll trade off every other clock period. If you didn't do that, one of them would get locked out for the length of time there. So that's how we resolve this. What about the, I said there was 3. Is there another one? Section conflict. How long does that last? What is a section conflict? Getting data out, really, yeah. But is it a port conflict? Yeah, that's what I was looking for. It's inside one CPU. In other words, you couldn't have a section conflict between CPU 0 and 1. Why? Because both CPU 0 and 1 have their own path, their own ports, don't they? So they both have their own paths out of memory or into memory. So that can't happen. But CPU 0 has only one path out of any one section. There's only 4 paths out of memory to CPU 0, and those are 1 for each section. So section 0 has one path out into CPU 0, section 1, 2, and 3. And that's the ZE modules, the error correction modules, is that path. Now, since this is going to be a 1 clock period conflict, if you both want to use the same section, or two ports want to use the same section, there's got to be some means of resolving the conflict, doesn't there? Well, the way they did this is they said when you do a vector read or a B register read or write, you can have an increment on those instructions. Your increment could be an odd or an even number. For example, if you're reading data out of a memory into a vector register, your increment could be any number, 0, 1, 2, 3, 4, anything. If it happened to be 32, that was the instance I was talking about before when I'm always going to bank 0. And that's a possibility. Maybe you wanted to go to bank 0, and then you want to go to bank 40 octal, which is back in bank 0 again, and then 60, and then 100, and then etc. and get those words. For some reason, that's where your data was. Well, like what I said before, we try to keep the most efficient means possible of accessing memory. And that is not real efficient. Not as efficient if you have an increment of 1, where you're going and getting words 0 and 1 and 2 and 3 and 4 all the way up through 64. It's much more efficient. With this increment of 40 octal or 32 decimal here, I've been going back to bank 0 all the time. I've been waiting on the bank conflict that I created every time. So it's less efficient. So what they said is, when we have a section conflict, let's let the most efficient go first, and that's the odd number increment. So there's a priority scheme in that an odd memory increment has first priority. Let's see. Let me move this over so everybody can see it. The first priority goes to the odd numbered increment. Well, what if both references have either an odd or an even? If the increment is the same, then, if the increment is equal, in other words, they both have either an odd or an even increment, the oldest reference goes first. So in other words, the one that issued first will go first in this section conflict. So that's how we resolve the conflict. Since one CPU can only issue one instruction at a time, one instruction's always older than the other. So it's first come, first serve if you have equal increment, or first issued, first to memory. So that's about it for our review of what we did yesterday, except I threw a few little extra things in there. Any question on that? One of the things I said, but I didn't really stress, is that there's the data paths out of memory. There's one for each section per CPU. So that means section 0's got two data paths. Section 1 has got two data paths, one for CPU 0, one for CPU 1. And when I'm talking about CPU 0, I'm talking physical CPU 0 up here, the top CPU. And CPU 1 is the bottom CPU. That's physical CPU number. You can call, or there's a way to call either CPU 1 or 0, or processor 1 or 0. So there's a logical number and there's a physical number. The physical number is always CPU 0 up here. Logical processor number, either one could be CPU 0 or the first. There's a reason for doing that for software. If you have to, 0 always has to be in charge, and so you have to tell one of them to be 0 and the other one to be 1. You might want to swap the way they're called for software reasons.